YouTube videos of the break, and it's just taking way too long. All right, so let's go from current slide, which we already did last time, if it'll ever come up. Oh, I hit the wrong key. No wonder it wouldn't come up. And while let me go on to mark the roll first. Daniel's here. Sarah's here. I think Mike had turned in some stuff. So we'll go from there. All right. Let me hit these announcements. Are any of you graduating this term? Not this term. Okay. If you know of someone who is, okay, there are two really nice scholarship opportunities out there that they sent us this email yesterday. No, I'm sorry, Tuesday. And the deadline for the first part of this is Monday, okay? And the second part is Thursday of next week. So tell people to check your emails because it's went to all students. So check your student emails if you know someone who's graduating this term. Now, are any of you walking this term? You know, in other words, you won't finish till summer, but you're planning to walk in May, because we only have one graduation ceremony a year. Okay. If you know of anyone who is, again, this went to all students on some meetings. There's two on the Birmingham campus, one on this campus next week, Monday, Tuesday, and Wednesday. Mondays in the evening on Birmingham, Tuesdays in the afternoon here, and Wednesdays in the afternoon on Birmingham. All right, the math team, Mr. Gerasi is still looking for participants. If you can, they meet Friday at noon in room C100 in the Birmingham West Campus, and then they meet Monday evening or afternoon at 3, also in C100 in the Birmingham Campus. Now, today we have some training that's going on, and that's going to be from 2 to 3:45 today. So if you're looking for me today, between 2 and 3:45, I may be down there in the training, okay? Now, if I go down there and the room is packed down full, I'm going to let the younger folks go to the training. I'll go back and get work done in my office. But if they need people to be there, I will be there, okay? Those younger folks are going to be out here a lot longer than I am, so they can probably use the training. Now, I think I announced to you before about the tutoring schedules on both campuses, okay? But if you need tutoring, you certainly can take advantage of it. But all of you seem like really good candidates to do tutoring, so if you're interested, Student Support Services, Ms. Hollins on this hall in room 202, or downstairs in room 105 is the Space Center tutoring. Both of those pay pretty well. You know, at least minimum wage, I think a little bit more, and they're fairly flexible in their hours. Another one up here is, I think that one down there is too. And then they have other opportunities on the Birmingham campus as well. This is homecoming week. Been activities all week long. Today, right after class, starting at 11 o'clock, is a cookout. Okay, there will be one on this campus and the Birmingham campus, so if you have to go over there, you can catch it there. The cookout here will be, I don't know if you know where the library is in this building, and if you go around the corner of the building, there is a little courtyard area between it and the B building. If you're coming in from the parking lot up there, you're up one level from that. And so there may be some activities in that entrance where you come in the building, but most of the activity is going to be down that set of stairs right next to it. So that's today starting at 11. If you have another class right after this one, there'll probably still be food when you get out of that class. Okay. On the Birmingham campus, I believe the cookout is at the Leon Kennedy building. That's where that. Now, that's today at noon. It'll be full lunch hour, or a couple of hours for lunch. Okay. This evening, they have the Cougar Choice Awards. That's happening at 5:30 in the A.G. Gaston Auditorium on the Birmingham East Campus. Okay. And that should be a lot of fun too. I think it'll probably go at least an hour, hour and a half, or something like that. Then tomorrow, okay, nothing much during the day, but in the evening. And by the way, the theme of this homecoming this year is back to the 90s, okay? And their ads that they put here show a lot of the sitcoms that showed up in the 90s. So if you did want to, dress up or do something either just for anything in the 90s or like some of the characters in the sitcoms, that would be fine too. But the party Friday evening is a party with a purpose. Okay, now it's not a 90s purpose. The purpose is bring some item that could be used in a shelter. Okay, that could be blankets, non-perishable food items, toiletry items, anything they may need at a shelter. Bring that. Admission is free. That's your admission. Bring the item. That's the purpose. The party goes from 7 till 9. Okay? And that'll be at the Leon Kennedy Center on the Birmingham West Campus in the cafeteria. That's on the main floor there of the Leon Kennedy Center. Then next Monday, wrap up homecoming with a homecoming parade and pep rally. That will be at 4 o'clock in the afternoon. And where they start at the A.G. Gaston building on the Birmingham East Campus. The police have already been, they're going to block off Wilson Road there. The parade will come through from East Campus, come over to West Campus, and I think they go to the gym, which is the Arthur Shores Fine Arts building. And that's, I think, where the pep rally will be. Maybe it'll be on both ends. I don't know. Okay? The homecoming games will be Lawson State versus Gadsden State. The women will start their game at 5:30. The men will have theirs at 7:30. Okay? And those are the homecoming games. And that'll be at the Arthur Shores Fine Arts building, which is also, by the way, the gymnasium, okay, on the Birmingham West Campus. So that wraps up homecoming next Monday. And I have a meeting or a training today at 2 to 3:45. Then next Thursday, they've scheduled a meeting, the Dean and Chair's retention meeting. They moved it to next Thursday, March 1st, from 2 to 5. So, and that'll be here in the Ethel Hall Auditorium. No, in the conference room. They're eating up my Thursday afternoons. So I know I'll be at that. I'll be at this one if there's room available. Okay. Well, I've been giving announcements, hoping other people would come in, but so far not. So let's get on. Any questions on anything in general or trig in particular? All right. Okay, where we're going to go from now, we did the damp trigonometric graph of example, well, it wasn't the example, that's before example 6. They don't show example 6. Well, they do. There it is. Okay. So here's example 6. Sketch the graph of f of x is equal to e to the minus x times the sine of 3x. All right. Now, there's a variety of ways to do this, and I don't want to stifle your creativity, but how would you start it? And if I think of a better way, I may stifle and say, we'll try it this way. Okay. Where would you begin on something like that? And there's a couple of places you can begin. So there's not one fixed answer here. How do we usually begin it? Say again? Yeah, your ABCs. It's as easy as 1, 2, 3. Okay, so how do we do that? What would be your A here? Okay, it's that variable function right there. That's the thing that's a little bit different about this. And you don't have to do it this way, but since y'all chose to, let's say the a is e to the minus x. Not a fixed number, but a variable. Okay? So we're going to come back to that in a minute. What would be the next thing you would do? B is 3. And what do we do with B? What does that relate to? The period. And what is the period? Okay, this is a sine function, so it's 2 pi over b, which is 3. So 2/3 pi. Okay? Now what do we do once we find the period? Divided by 4. And so if you divide that by 4, it's the same as multiplying by 1/4. And that would be, all right, the 10 o'clock scholar. Yes, okay. No. Glad you're here. All right.
2 pi over 12 or pi over 6?
Yes, okay. Divide that, and that would be pi over 6. The period is 2/3 pi. The interval that we're going to deal with is pi 6. C is 0, D is 0, so there's no shifts, either phase shift or vertical shift. So we're happy with that. All right, so at this point, I would typically draw my axes. Okay. And I would typically mark off my intervals. Okay? And there's a 0, of course. We'll do 1, 2, 3, 4, 5, 6, 7 maybe. Negative 1, 2, 3, 4, 5, 6. Okay? Now, vertically it gets a little stranger. We'll just do 1, 2, 3, 4, 5, 6, 7, 8, and negative 1, 2, 3, 4, 5, 6. Okay. Now, notice we said our amplitude is now a function of x, okay? E to the minus x. So let's plot that. Does anyone know how that looks? Or give me a few points of it anyway. Give me an x. 2, okay? Good choice. As good as any, I guess. So the a at 2 would be e to the minus 2, which is 1 over e squared. E, remember, is about 2.7 with lots of more digits following. So let's just, for funsies, just call that 3. I mean, it's going to be a little bit more. So since the 2 is less than that, the value of that is going to be a little bit greater. But that would be about 1 over 9, right? And, you know, I can't plot that very well anyway. 1/9 would be somewhere down about here, okay? I can't get my pen to operate. Okay, there it did operate. Now, give me another x. 1, okay, I like that one even a little better. A of 1 would be e to the minus 1, which is 1 over e, which would be about 1/3. So at 1 will be about 1/3. Didn't change a lot, but it changed a little bit. Give me another x. A at 0. What would that be? E to the 0, which is, second, 1. Okay, anything to the 0th power, except 0, which is not defined, is 1. So e, even though it's an irrational number to the 0th power, is 1. Okay? How about another one? Negative 1, and that would be e to the minus a minus 1, which would be e, which would be about 2.7. So at negative 1, we're going to be somewhere here about 2.7. And there's Jared. Okay? We have of our few and faithful here, so let's go with it. We're doing example 6, bottom of page 313. Okay? So that would be about 2.7. I didn't write that in. That was 1. Okay? This was about 1/3. Okay? It's not 1/3 really, but it's close. Okay? And this one was about 1/9. Okay? It's not. It's off from that a little bit. Want to do one more? -2. That would be e squared. E to the minus of -2 would be e squared, and that would be approximately 9. Okay? That one's going to be off scale, right? Because that was 3, 4, 5, 6, 7, 8. Yeah, it's off scale. So this curve here is doing something like this. Oh, I bet I messed that up pretty miserably. Sorry. Back off, folks. Okay, sorry about this. No, let's just erase this. I just realized I didn't mark my axis. And I was doing something really dumb here. Remember, I didn't mark the x-axis. I should have. Remember, this was pi sixths, pi thirds, pi halves. 1, 2, 3, pi. Okay, and this was -pi sixths, -pi thirds, -pi halves, and -pi. Now, the reason I should have done that, I was using the wrong scale. When a is equal to 2, okay, think about this. Pi is about what? Approximately 3.14, just a little bit more than 3. So pi thirds would be just a little more than 1. So 2/3 pi would be a little more than 2. That's where I should have put that first mark. That was about 1/9. It would be 2/3 pi. That would be about here. That should have been that one. And when it's 1, that would be about 1/3. So we'll put that about here. And then at 0, it's 1. I got that one right, okay? And at -1, that would be about -pi thirds. That's your 2.7, okay? So that would be somewhere about here. And the -2/3 pi, that's the one that's about 9. So here is my, ooh, I'm not drawing this very well, but that's what it would look like approximately. Okay, should be a little higher there. Catch that first dot. Okay. Now, here's the thing that you have to do with this thing. We don't just draw the upper part of the amplitude, because this is variable amplitude. We have to include the bottom part as well. So we mirror this across the x-axis. Okay? And that will be then down here about 2.7, -2.7. Here at -1, here at -1/3, here at -1/9, and this will be the lower part of our, yuck. Okay, let me start up here. We'll come along here, and something like that. Probably have too great a bend to it. Something like that. Quit that. Okay. Now, that's your envelope. That's your amplitude function, you might say. Okay? Now we plot the sine curve. Okay? And by the way, e to the minus x, this one up here, is always positive. So we're not going to do a thing to change the sign of the signs. They'll be plus or minus whatever they normally would be. So let's now plot the signs, and here we'll use the pi 6. Where does sine begin? At 0. And it reaches its maximum at the first interval, quarter period, which is at pi 6. Then it goes back to 0. Then it goes back to minus amplitude, back up to 0, and then back up to plus amplitude. And basically, from there on, it just does weird things. Back here, it goes down to the minus interval, okay, minus amplitude, up here to 0, up here to plus the amplitude, back down to 0 here, and then it's off scale, big time. So your function does something like, my drawing leaves a lot to be desired. Okay, and then from here it just wiggles back and forth, you know. That's what it looks like. Okay, it would have another 0 here, so it would wind up going down here and up here forever. Okay, so that's your dampening. Okay, I like to think of this, and the book doesn't use this terminology, but I like to think of that as my amplitude function. Okay, and that's what the amplitude is going to be. When this is getting huge, the amplitude is getting enormous. When it's getting small, the amplitude is acting back. Now, I probably did a really lousy job on this. That was a 0 there, max here, a 0 here, min here, and 0 here. So I shouldn't have had so many squiggles in there. But it doesn't matter. It's getting so small you can hardly see it. That's why they call it a damping function, because it's damping out the amplitude like crazy. Okay? Now, if you flip that around and done e to the x, then it would be magnifying the amplitude like crazy as you go to the right. And then your damp part would be down here. Does that make sense? All right, good deal. Any questions on it? There is a checkpoint. Please, if you think you need a little practice or doing with this, that's a very similar one. That has e to the x, so it's going to be getting big positive rather than getting small positive, and it's a different period there too, so it's well worth a look. And if you need help, LarsonPrecalculus.com has audio-video solution to it. All right. Now that's my chicken scratch. Let's see what they did. I'll erase all this unless anyone needs it longer. Okay. So let's consider f as a product of two functions, e to the minus x and sine 3x. Yeah, that's exactly what it is. Okay. Each of which has a set of all real numbers as a domain, so no sweat there. For any real number x, you know that e to the minus x is always positive. When we graph that, we saw that. And the absolute value of sine of 3x is always less than or equal to 1. Okay? Yeah, sine stays between plus or minus 1. Okay? So e to the minus x sine, absolute value sine 3x is always less than or equal to 1. Basically what they did, they took this function and multiplied it by this inequality. E to the minus x sine 3x is less than or equal to e to the minus 1. Okay? So 1 times e to the minus x. And that's a legal thing to do because this thing's always positive. So it doesn't change the sign of the inequality. Now you can take the absolute values off, and that means that minus e to the x is going to be on this side of it. So this is what they get. Okay? A lot of writing to get, okay, it's fine. It's perfectly fine. But this is why we plotted we plotted e to the minus x to be our upper envelope, and when we did minus e to the x minus x to be our lower envelope. So this is justification for putting them on both sides, that mirror image. And then the function's got to be somewhere in between that envelope. Okay? And then they did their thing with the just sort of irritates me how they do this, but where your maxes are mins, that's going to be where 3x is some a 2n pi multiple of 2, an n multiple of pi thirds. Okay, so They only show one place there, but it's going to be plus or minus n pi. Okay. The max or mins are at the first interval. See, that's why don't you do the period, do the interval, that gave you pi 6, okay? And that's going to be your first max, and then all your maxes or min are going to be in intervals of that. Just, what we did before. No, those are, that's only going to give you your maxes. It's not going to give you your mins, okay? The mins would be at the other one, so I would have left that as plus n6 pi. Okay, no. It's just an awkward way to do it, okay? But it's right. It's perfectly correct, okay? And then your zeros are going to be at the n pi's, okay? N periods, okay? And that's going to be 2n. This is where we get your period. 2 pi over 3. That gave you your period. So these are going to be half of those because you have a 0 in between each one. So it'd be n pi over 3. Okay. Really an awkward way to do it. Okay, but it works. And here's the graph, and you see very similar to what we had. This thing blows up rapidly out here. It narrows down very rapidly here. You have a 0 here, max, 0, min, 0, max, 0. It's hard to see anything beyond that. And then going this way, a min, max, and then a min somewhere down here, and then it goes back up and blows up really fast. Okay? And that's why we plotted our e to the minus x up here, minus e to the minus x here, because it stays in between. I like to call this the amplitude function, okay? Because that's what your amplitude is varying as you go, okay? The book doesn't like or use that terminology. It seems like to me that makes sense because it fits all the patterns we did before. Okay. That's just my weird way of thinking. Okay. Now, we're no longer talking about damped trigonometric graphs. Y'all may be, but I'm not. Okay. Here's a summary of the characteristics of the 6 basic trig functions. Okay, sine function, just plain old sine x, the parent function, sine x. Going to say between plus or minus 1 on y, have a period of 2 pi, so an interval of pi halves. Every pi halves, you're going to go from 0 to max to 0 to min to 0 to max to 0 to min. Backwards and forwards, 0 to min to back, 0 to max. Domain, all real numbers, range plus or minus 1, period 2 pi. What else can you say about it? Reflects across the origin, which means it's an odd function. Okay? Now, cosine looks just like it except for a phase shift. Move it back half pi, and you've got the cosine. It starts at 1, it goes down to 0, down to minus 1, up to, okay. There it goes. Its domain is again all real numbers, range plus 1 to minus 1, period 2 pi. But what is it? It reflects across the y-axis, which means it's an even function. You got it. Okay? Now, with that in mind, your tangent function is sine over cosine. So if you think about it point by point, that would be 0 over 1, which is 0. And this would be 1 over 0, which is undefined. And this would be minus 1 over 0, which is undefined. So that means the tangent function is going to be undefined at the half pi's, every half pi, wherever cosine is 0, because that's in the denominator. And it's going to go negative on this side, positive on this side. Your a in that case, which in this the tangent function up there. Here's the tangent function. The a is going to be, there's a is 1, so if the quarter period, the period is pi, the quarter period is here, it's going to be plus 1 here, minus 1 here. So you don't have an amplitude anymore, but we still use the A to identify what's happening in the quarter period. And your zeros here going plus or minus infinity. So vertical asymptotes everywhere. Domain is all real x's except your half pi's. Okay? Range is from negative infinity to infinity, and the period is pi. What kind of function is it? Pi, which means it reflects across the board. Now, here's the cotangent function, which you can either think is 1 over tangent. I usually think of it as cosine over sine. Okay? So therefore, I think everywhere the sign is 0, you have a vertical asymptote. And signs are 0 at the whole pi's. Okay? I like whole pi's. Okay? But the so the vertical asymptote is going to be at the whole pi's, and everything else is pretty much like tangent, except tangent's always increasing as long as it's a positive tangent, and cotangent's always decreasing as long as it's a positive cotangent. And what can you say about the reflection? Across the origin, which means it's also an odd function. Okay? Domain is all real number x's except the whole number of pi's, range from negative infinity to positive infinity, period is pi, just like tangent. Okay? Make sense? And then the secant and cosecant, they didn't draw in what you would draw in first, the corresponding sine and cosine. Everywhere that sine is 0, your cosecant is undefined, so that's your vertical asymptotes. X can't equal n pi, just like it was for cotangent, because cotangent was cosine over sine. So you have the same vertical asymptotes, but here you have a difference. If you had drawn the sine function in there, you knew that those zeros were going to be your vertical asymptote. Your min is going to be the max here. The max is going to be the min there. Max, okay. So you flip everything over, kind of. So your range is from positive 1 to positive infinity, from negative infinity to negative 1. Period, because it comes from the sign, is 2 pi. Now, what kind of function is that? Odd function, which means it reflects across the origin. Okay? Then the secant function, which is 1 over cosine, will have the same vertical asymptotes as tangent, because tangent is sine over cosine. So everywhere the cosine is 0, you get your vertical asymptotes. That's why we usually plot the cosine first here. At every 0, you put your vertical asymptote. At every min here, you're at the max of secant. At every max for cosine, you're at the min for secant. On and on. And they go toward the vertical asymptotes. So the main is all real numbers except your half pi's. Okay? The range is just like it was for cosecant, from negative infinity to negative 1, and union that from 1 to positive infinity. Never takes on a value between minus 1 and 1. Okay? Period is 2 pi because it's similar to the cosine. And what about its reflection? Second? It's an even function called the reflection of the y-axis. Okay, good deal. Any questions about those? That then wraps up, sorry. Wow. 4.6. So let's look at the vocabulary for 4.6. The tangent, the cotangent, and the cosecant functions are blank, so the graphs of these functions have symmetry with respect to blank. They're odd, so they have symmetry with respect to the origin. Very good. Number 2, the graphs of tangent, cotangent, secant, and cosecant functions have blank asymptotes. Vertical asymptotes. Number 3, To sketch the graph of a secant or cosecant function, first make the sketch to its blank function. Reciprocal function. Excellent. Okay. Number 4. For the function f of x is equal to g of x times sine of x, it doesn't have to be sine, it could be cosine. Usually don't do secants, cosecants, and don't mess with those. But usually sines are cosine. G of x is called the blank factor. Second, damping fraction, the exact factor. Okay, number 5. The period of y is equal to tan x is blank, pi. The domain of y is equal to cotangent x is a set of all numbers such that blank, cotangent x. Set of all real numbers such that x is not equal to the cotangent, which is cosine over sine. N pi. It's a multiple of n pi. Exactly. Number 7. The range of y is equal to secant x is blank. Got it. The period of y is equal to cosecant x is 2 pi. Perfect. Okay, homework exercises. I said this before. I would do all of 9 through 14 because they're just easy matching things. The trouble is you only have answers in the back for the odds. So check your answers for the odds. If you got some of those wrong, then you probably got some of the evening ones wrong too, possibly. Okay? Then do any of the odds, 15 to 37. All those odds have worked out solutions, tutorial help and worked out solutions at calcchat.com. They have the answers in the back, but then they have worked out solutions tutorial help at calcchat.com. 19 has further help at calcview.com. Then do any of the odds 39 to 47. They're all at CalcChat. There are none of those at CalcView. Then do any of the odds 49 to 55. All of them are at CalcChat. 51's at CalcView. Do any of the odds 57 to 63. They're all at CalcChat. 57's at CalcView. And I would do all of 65 to 68. Again, that's matching. But I would, the answers in the back and at CalcChat are only there for 65 and 67. Okay, there's a conjecture here, and you can do either 69 or 71. Both of those are at CalcChat, neither at CalcView. Goodness gracious, for some reason I'm losing energy like crazy. I had my first day that I really felt pretty normal yesterday. Most of the day. I got a little tired, like walking up half flight of stairs. Like, goodness gracious, yeah. But I stayed here. But then I think I may have overdone it. And so today, this morning, boy, it was rugged. Okay, 73 or 75. Both are at CalcChat. Neither are at CalcView. Then do any of the odds 77 to 81. They're all at CalcChat. None of them are at CalcView. And then some applied problems, 83 or 85. Either one of those, both of them should be at CalcChat for worked out solutions. Okay, exploration, 87 is a true-false. Think through that. 89 is another think about it. 91 is some graphical reasoning. And 93 is more graphical reasoning. Okay? You can do any of those if you want. I assume that most of those are at CalcChat and in the back of the book. But I don't know if they do all those there. All right. Any questions on 4.6? Where did my... Everything just went blank. Okay, it came back. gracious, that's scary. All right. So let's move to 4.7. I know you'll be very disappointed. We're through with graphing for now. Though we'll use graphing in lots of places. But those two sections, 4.5 and 4.6, were our graphing sections. And believe me, your test will reflect that. About half the test is going to be graphing. The rest of it will be more calculations, like we'll be doing in 4.7. Okay? So let's get our slideshow set up for the current slide. Man. Not certain I'm going to make it today for the full 9 hours I usually try to work. I'll make it as long as I can. I may not make that training session this afternoon. We'll see. Okay. So we're still in Chapter 4, Trigonometry. The measurement of triangles is what that word originally meant. And 4.7 is inverse trigonometric functions. Now, what do we mean by inverse? Does anyone remember from Math 112? An inverse function is one that undoes another function. That's one way to look at it. Okay? So what we're going to be looking at are functions that undo what a trig function would do. Now let's think about what a trig function does. What's your input or your domain for a trig function? Any of your 6 trig functions. They're usually, though the book makes a special point of calling them real numbers, but they usually represent some type of angle, right? That's what you take the trig function of, an angle, right? And what's your output? The range. Some number that's associated with that angle, right? Remember on your unit circle, for the sine, the output was the input was your angle, the output was your y variable. Okay? Then when we moved on to triangles, it's the ratio of opposite to hypotenuse. But it's just a number, okay? Get input an angle, output a number. Now, so if you're doing an inverse trig function, what's your input going to be? Okay, a number, and your output's going to be an angle. Now, an angle is also a real number. I mean, in radians especially, those are just real numbers, okay? But this helps me get it straight because an inverse function undoes its inverse, okay? And if the trig function operates on an angle giving you a number, then the inverse trig function operates on the number and tells you what angle produced that number. So I like to think of it in that way, okay? So what we're going to do, I said we were through graphing, I'm just kidding, evaluate and graph inverse sine functions, okay? Evaluate and graph the other inverse trigonometric functions. And believe me, we're really only going to do cosine, tangent, and cotangent. I don't think we'll ever do an inverse secant or cosecant because those pick up and go in weird ways. You can do it, but it's just a little bizarre, okay? And we'll evaluate the composition of trigonometric functions, okay? Composed trigonometric functions, which could have been in the last section, but we chose to put it here, okay? They chose to put it here. So let's start with the good old inverse sine function. We know that for a function to have an inverse function, what must be true about it? It has to be a one-to-one function. Excellent. Okay, you remember that from 112, right? Okay, what do we mean by one-to-one function? It's what? I can't do this one.
It doesn't like have two x's on the same.
Okay.
It passes some kind of vertical line.
that's any function passes a vertical line test. A one-to-one function also has to pass a horizontal line test. So in other words, it can't back up on itself. So it's either going to be strictly increasing or strictly decreasing. To be a one-to-one function, it's got to have that. It must pass the horizontal line test. Okay? Does the sine in general pass a horizontal line test? No. Okay. So what you have to do with the sine function is limit it to a specific domain for the sine that is strictly increasing. You could have chosen this and be strictly decreasing, or this one be strictly decreasing, but we like to hang around the origin. That's, so we'll choose that portion right there. So that portion there is the only portion of a sine function that is one-to-one. Well, it's not the only one that's one-to-one. It's the only one that has an inverse, and it's only on that interval. Okay. Now remember the other thing we do, we exchange the x's and y's. So your domain of your sine function is from minus pi halves to pi halves, including the endpoints. The range of that is minus 1 to 1. Okay, that's always. When you do the inverse sine, then your range is going to be, your domain will be minus 1 to 1, and your range will be minus pi halves to pi halves. So things reflect across the identity function. Basically, is what we do. Okay. So it does have an interval, but an inverse function, but only on that interval. It doesn't forever, only on that interval. Okay? However, when you restrict the domain to the interval from minus pi halves to pi halves, corresponding to what we're just looking at, then it has an inverse. On that interval, the function y is equal to sine x is strictly increasing. So that means that, and by the way, the name for that is monotonic. Monotonically increasing or monotonically decreasing. Okay. On the interval from negative pi halves to pi halves, which includes the endpoints, by the way, y is equal to sine x takes on its full range of values, minus 1 to 1. You don't lose anything by taking on that. You have all your outputs. And third thing is on the interval from minus pi halves to pi halves, sine y is equal to sine of x is 1 to 1. Okay? Yeah, that's where we started. That's where we ended. It has to be either strictly increasing or decreasing to be 1 to 1. And it really has to have all of its values there too. So it's a 1 to 1 function. Okay. So on that restricted domain from minus pi halves to pi halves, y is equal to sine x has a unique inverse function called the inverse sine function. What a clever name. Okay? Now, it's denoted two different ways. One is by the old term, or at least to me it's the old term, arc sine. And what I think that means is associated, related, close function. It's a weird thing where they get arc sine. You just call it arc sine. I like the thing because this is how we did in Math 112. If you had a function f of x that was 1 to 1, it had an inverse, which is f to the minus 1. So I like to call it sine inverse sine. I'll read that as inverse sine. I'll read this as arc sine. They mean the same thing. So the notation sine to the minus 1 is consistent with the f to the minus 1, which is what we call it. Warning! Don't think of this as 1 over sine or this as 1 over f. When you have a function to the minus 1, that doesn't mean 1 over. If you have a variable or a number to the minus 1, yeah, that's what it means. But that's not what it means if it's a function. So this sine to the minus 1 means inverse sine, which means inverse function. Okay? The arc sine notation, read as arc sine of x, comes from the, and here's what it is, the association of a central angle with its intercepted arc length on a unit circle. Oh, that makes it clear, doesn't it? Yeah, okay. Whatever. Okay. 2 slides from now, I won't even be able to tell you what that said. Okay. Probably 1 slide away. Okay. So the arc sine means the angle or the arc whose sine is x. Okay? That's exactly what I was saying. Remember, we exchanged the x and y. So when you have y is equal to sine x, that's your angle, that's your number that's associated with the angle, the ratio, whatever it is that's associated with that angle. So when you have the inverse sine, that's your number, that's the angle associated with that number through that sine function. Okay? That helps me remember and understand that. So the arc sine means the angle, that's going to be your angle now, whose sine is x. In other words, you take sine of y, you get x. Take the inverse sine of y, you get x. Okay? You just reverse the variable and do the inverse function of it. Okay. So both numbers, both notations, arc sine and inverse sine, are commonly used in mathematics. So remember that sine to the minus 1, that's a function to the minus 1, denotes the inverse of the sine function rather than 1 over sine. What do we call 1 over sine? Identity? Reciprocal identity? Remember? Yes, that's what 1 over sine is, so don't think of that. Yeah, I probably shouldn't. It's like saying, don't think of a big black horse, okay? What are you thinking of? Big black horse, okay, yeah. Probably they shouldn't have even said that, but don't ever think of that. Okay. So, the values of the arc sine function, that's the output of the arc sine function, has got to be those. Were your angles for the sine, they're now the output for the arc sine. So that's from minus pi half to pi half inclusive, the equal signs are in there. And the graph of the arc sine function is just like this. Remember what was your domain of sine, 0, negative pi half to pi half, now is the range of your inverse sine, or your arc sine. What was your range of the sine function is now the domain of the arc sine. You can't go outside of those. Now, this portion here looks about the same no matter how you do it, okay? But before you reach the minimum here, went through 0 there, and the maximum here. So now, rather than that being a 0 slope, it's an infinite slope, okay? Up here, and that was another 0 slope, 1 over 0 would be an infinite slope there. So that's what the inverse sine looks like. Okay? Now, I'm not going to be able to do this well, but I'm going to try to do it anyway. Come over here and do it. Yes?
Hey, I can't get my quiz.
For what class?
8 o'clock.
Okay, the Math 112?
Yes, sir.
Okay. Do you need graph paper?
Yes, sir.
There's the quiz. Let's see if I have any spare graph paper. Yeah, there's one.
Okay, thank you.
Okay.
Bring it up Tuesday.
I'm sorry?
Bring it back Tuesday.
When you finish it, yeah. I can't believe you come in and interrupt the class. Get over it. Okay. All right. All right, I've already got red up here because we just changed. Remember your good old one-to-one, your identity function? It goes from -1, -1. The thing is, this is minus pi has, which is about -3. So it's going to be something like that. Okay, that's not very good. Like I said, I can't draw this well. Reflect that over that, and you wind up with something like this. Okay, now that's not drawn very well. Or, doing it the other way, take, did I not skip one? Yeah, okay. Let's go back to my red here. Okay. One. Okay. This is so tedious. Okay. Something like that. And reflect that, and you have something like okay. So in other words, they reflect across the x-axis. Like I said, this line here is almost the function as it was. That middle section, so no matter which way you start, that's going to be the same. It's just that this one's curving down, this one's curving up, this one's curving up, that one's curving down. It just reflects across there. Okay. I don't know if that was helpful or not. If you remember back, that's what inverse function does. It reflects across the identity function, which is y is equal to x. Because what you do, you exchange x and y. That's what inverse functions do. Okay. Now, any questions? All right, so here is your actual definition of your inverse sine function. The inverse sine function is defined this way: y is equal to arc sine or inverse sine of x, if and only if, when you take the sine of both sides, that makes sine y equal to sine of arc sine, which undoes itself and just leaves you x. Remember, inverse functions undoes the other function, where your x here is between plus or minus 1, because that's the number, and your y is the angle corresponding to that number between minus pi half and pi half. Okay? The domain of the inverse function or inverse sine or the arc sine is between minus 1 and 1, which was the range of this function. Okay? And the range of the inverse function, or the arc function, is minus pi half to pi half, which was the input of this one. Make sense? All right, so let's do these. If possible, find the exact value of inverse or arc sine of negative 1/2. Okay. Now, the book has a strange way of doing this. It's absolutely correct, but I don't care for it quite as much. Here's what I like to do. Okay? If I see that we're doing an inverse sine or arc sine, then let's assign that to some variable name. What do you want to name it? Pick a name, a letter, a variable, variable, anything. Greek, not Cyrillic. I don't know Cyrillic. Okay, English will be fine. I don't care. Pick a variable. Anyone will do. X. Okay, why not call it X? Okay. Now, what I like to do, since this is what I'm looking for, I'm looking for that value. Okay. I like to then write the equivalent equation to this, but not with the inverse function, but with the function itself. So what would be its equivalent equation? Okay, let's go back to this. If y is equal to arc sine x, we name the x equal arc sine negative 1/2, if and only if the sine of this is equal to that. Okay? So you tell me what to write here. Sine of x is equal to negative 1/2. You got it. This is how I like to do these. If they're in inverse or arc sines, rewrite, assign a variable to it, make up a variable, whatever you want to do, and then write the trig function that corresponds to that. Now let's solve that for x. We've done that before, right? Okay? Now here's where I like to draw little pictures, okay? I don't draw very nice little pictures, but you live with them, okay? Here is my thing. Sine is what? Basically, sine is, what's your definition? Some old hen. Don't you remember some old hen? I told you that. Oh yeah. Old as old. Exactly, okay? And opposite is usually which are your variables? If this is, now these are not the same x's and y's you have up here, but if you had this, opposite is the hike, okay, okay, is the y variable. The adjacent is going to be the x and the opposite is going to be the y. So this would be a -1 in y and 2 on x. So let's just draw our, since this is the hypotenuse, that's going to be my radius. So 1, 2, 1, 2, 1, 2, 1, 2, okay? So let's draw our circle. It's not a unit circle, it's a 2 circle, okay? Because the radius is 2, but your y is going to be -1. So that puts you down here somewhere. My circle is not very pretty, but somewhere here, okay? So what we're looking for is this angle right there. That's going to be my x. We'll give you a -1 for your y and a 2 for your x. Because the hypotenuse is always positive, right? Now, what angle will that be? Anyone remember? I know it was several sections ago, but as soon as we're through, we're Etch-a-Sketch, shake the screen, and it's gone, right? No, we don't do that. What angle would that represent? What's that? Okay, yeah. Here is your right angle right here. Okay, right there is the right angle. What is this angle here? Okay, there's your right angle. We're looking for this angle. Angle whose, okay, let's do the reference angle for it. The opposite is 1 over the hypotenuse is 2. Say again? Yeah, your x is this angle right here. Not the x on the screen, not this x. That's why I wish you had chosen something other than x. Let's go back and name it theta. Would that be okay? Okay, that won't be confusing things as badly. Okay. I should have stopped you at the moment you said it. Okay. Let's call it theta. Okay. This is your angle theta. Okay. What angle theta is that?
So it's opposite over hypotenuse.
Yeah, opposite is -1 over hypotenuse of 2. Yeah. Section 4.1 or 4.2, we were doing these spitting them out. Okay. Remember we said we had some favorite angles. One was the square root of 0 over 2, square root of 1 over 2, square root of 2 over 2, square root of 3 over 2, square root of 4 over 2. Remember those? square root of 1 over 2 would be that, and this is the opposite of that. What was that? You can give it to me either in degrees or radians. We know they're our friends. 30 degrees. Or pi over 6. Yes. So this will be negative pi 6. If you like a dentist. Okay. So what is your theta? The theta is negative pi 6. Okay. Let's try the next one, okay? All right. Where would you start it? Second? Okay, yeah. But here's what I like to do. Since you know this is an inverse sine, what here is the number, and what's that going to be equal to is in? Angle! Very good. And that's why I like to use the Greek alphabet there. It doesn't have to be theta, but that's everybody's favorite. So let's name this. Do you like theta, or would you rather have a different one? Okay, yeah. Good theta, good theta. Okay. All right. Let's rewrite that equation with the trig function rather than the inverse function. And what would that be? Sine of theta is equal to square root of 3 over 2. Perfect. Now, let's use that same 2 circle here, okay? We'll just take this out and that out. Okay, I can't get it all out without losing it all. Okay. Square root of 3 over 2. That's going to be somewhere up here. That's going to be your right angle then. We're looking for that angle theta. You want to know what that one might be? Square root of 0 over 2, square root of 1 over 2, square root of 2 over 2, square root of 3 over 2, square root of 4 over 2. Huh? Square root of 3 over 2. What angle is that going to be then? And I did this sort of on purpose. Second? 6C, which is? Twice 30, by the way. 5 or 3 pi over 4 would be somewhere over here. Okay, we're up here. Second? Second? Pi thirds, exactly. Twice pi 6. Pi thirds. Okay? So theta equal pi thirds. Okay? All right. How about that next one? Inverse sine of 2. Okay. Want to name, okay. Since you're doing an inverse sine, the input for that is a number, 2. The output is going to be an angle. What you want to name it? Theta. All right. What a clever name. Okay. Equal theta. Now write an equivalent equation for that. Sine of theta is equal to 2. Now, what angle theta produces a sine of 2? Okay. What's the range of sine? It can't happen because that's outside the range of sine, isn't it? So notice here it said, if possible, This is not possible. Right? Yeah, you can't do it. There can be none. Because the domain of an inverse sign is -1 to 1, just like the range of sine is -1 to 1. That's outside the domain. Okay? If you tried that in your calculator, that's what it would do. Invalid domain. Okay? Make sense? Now, notice here, because we're restricted to one-to-one function, our angles that we deal with here are only from -π-halves to π-halves. We're only here. So if you have a minus, the minus is going to be on the y, never the x. Don't go over here. It's the y. Now, oh my word, we're almost out of time. How could it happen? Let me erase my scratch here, and let's see how the book does this. Now, this to me is ludicrous. I mean, it's true, because the sine of -π-halves is π6 is -1/2, therefore, and negative π6 lies in the domain, therefore that's the answer. So basically, because this is the answer, that's the answer. I mean, I'm going to go, what? You know, where to me it makes a lot more sense to name an angle and then figure out the angle and say, yeah, because that's true, that has to be the answer. Okay? And that's where pictures help and that kind of stuff. So, you know, that their logic here is absolutely correct, okay? But you have to know the answer to make it work. So how do you find the answer? Guess? You know, no. Just set up, let that be an angle, and then figure out what angle that is. And you maybe are guessing. It seemed like sometimes you were. Okay. And the next one, same thing. They say, because this is true, that's the answer. Yeah, okay, we'll buy that. But how did you get that? Okay. I hope that my way showed a little bit of how to get it. Okay. And that was not possible because no angle whose sine is 2. Sines are always between plus or minus 1. All right, remember the domain of the inverse sine function is -1 to 1. That's the other way of saying the range of the angles are plus or minus 1. So there is no angle to give you 2. All right, we'll pick up next time with example 2. Okay? Let's see, we got enough done to do a few homework exercises. Let's see what they would be. Any of the odd, let's see. Do number 5, and that's also on Calc Chat and Calc View. Number 11 and number 17. And we'll stop there. Well, yeah, we'll stop there. We'll pick up the rest of those next time. Okay? Good deal. Any questions? Second?
Say, Tuesday.
Yeah.
So you're ready to still take my test?
Yeah. Did you get it or not?
What?
Did I give you your test?
Yes.
Okay, yeah, I'll take them anytime. Yeah. In fact, I think you're only the second one to turn it in. Okay, good deal. Thanks. No, I've had more than that, but yeah. Good deal. Thank you. All right. Have a good weekend, folks. Happy homecoming. Okay.